work this time. So welcome to the third lecture in the HoTTEST summer school. Today, Emily Riehl will give, let's see, the sixth lecture on HOT, if my count is correct.
I think that's seventh, actually.
So please go ahead, Emily.
Great, thanks so much. Let me open up screen share. I'm impressed with those of you who are sticking with this. I know this is a lot of material coming at you very fast. I'm going to try and squeeze in a little tiny bit of a review today where possible. And a final thing to note for posterity is that there are lecture notes for the entire series that are on the GitHub, the summer school page. There's a link that I've just dropped in the chat for those of you who are here now. And there's some studies somewhere that says that people learn things or remember them better if they're handwritten badly. So I'm going to badly handwrite things that are typed up much nicer in the lecture notes. So you can choose to follow in whichever medium you prefer. Okay, so today I'm going to tell you about something that's called the fundamental theorem of identity types. And essentially what it is it's a way to recognize an identity type family in the wild. If you have something that you would like to be an identity type and you want to give a proof of that, characterizing it up to equivalence, which is the way we identify families of types in homotopy type theory. This will be the theorem that you'll allow, that will enable you to do that. So we'll see a number of applications. But before we get to that, let me start by just talking about what, I guess we'll call this the first section. So what, in fact, are identity types? And the reason that I'm asking this question is we've seen two different points of view on identity types, and I'll start by presenting them. These could be thought of as sort of two different philosophies of identity types, two different perspectives on identity types. And the first perspective, so this is the first point of view, number one, is that Per Martin Luff provided us rules for identity types, gave the following rules. Rules that defined identity types or identity types. And these rules apply for any type in any context. So for any type, I'll give the type a name in any context. I will not give the context a name because it's going to be sort of silent from here on out. And what's kind of remarkable about these rules is they're really uniform. They're sort of polymorphic in the type. It doesn't matter what sort of type it is. These rules will identify or will characterize its identity types. Okay, so the first rule was the formation rule, which is that there is a type family sort of given any terms x and y, two terms of a common type, then x equals y is a type. So I'm presenting these rules rather informally. And you might recall that the role that, or one of the roles that types play in type theory is they're formulating mathematical statements. So the way that I think about that is that it's meaningful to ask the question whether x and y can be identified once x and y are terms that belong to a common type. So the formation of this type says that it's a mathematically meaningful thing to try to do to identify x and y. Of course, just because you have the type doesn't guarantee any terms. So it might well be the case that x and y have no identifications, but it would be meaningful to wonder whether they do. So for instance, people on the internet love to debate whether 2 + 2 is equal to 4. That's a meaningful statement that you could ask. Okay, and as terms of type of natural numbers say. All right, so the second rule says that for any term x in A, there is a term ref x that inhabits the identity type that identifications from X to X. So this is saying, I mean, one interpretation of this is it tells us that the mathematical statement X is identifiable with X is true, and there's a canonical proof that's given to us, which is a reflexivity proof. So these are the formation and the introduction rules, by the way, that are characterizing this identity type family. All right, and now somehow the complicated one, the most powerful one, is this elimination rule, which says that which tells us how to use identification. So what can you prove with an identification? So for any family of types P, X, Y, P, that's allowed to depend, but of course doesn't necessarily depending. So depending on two terms, X in A, Y in A, and then an identification between them, or a path from X to Y in A. Path is kind of a metaphor for identification. So I'll phrase it like this. To inhabit the type, or really to prove the type, which is the dependent function type, into here. So to prove for all X, because we read these pi types as for all Y, and for all identifications between X and Y that P, X, Y, P holds. So in other words, to construct a dependent function or to prove this implication, it suffices to prove, or it suffices to inhabit the type, which is asking only to prove for all, maybe I'll change my variable, Z and A, that P, Z, Z, REFL, Z holds. So informally, this says to prove that for any X, for any Y, for any little p, that PXYP is true. It suffices to just prove a special case where Y is the same as X and P is the reflexivity identification. Another way to package this up, and this will be particularly, well, a little bit useful later and particularly useful next time, is that there's a term in this implication. So I'm going to write the hypothesis here, which is that for all Z, P, Z, Z, REFL, Z holds. And what this elimination rule is providing is a term in this function type that would take a proof, a section of the first type family, a proof of the special case, and then give a section of the full type family. So that's a proof of the general case. And the other hot book calls this function path induction, and I'm still kind of partial to that name, though the term identification is kind of taking over for path because it's a little more general. Okay, and then the final rule is the computation rule, which tells us the following. It says for any dependent function that inhabits the domain here, so any D that provides a proof for any Z and A that P, Z, Z, REFL, Z holds. Then I could apply this path induction to my term D, and that's going to give us a dependent function in this second type. So that's for all X, for all Y, for all P, a term type P, X, Y, P. And if I take for my X, let's say Z, and I take for my Y also Z, and I take for my P the reflexivity path, then that term is definitionally equal to DZ, which is the original proof that's given sort of for any Z of type A. And it's hard to know what symbol to use for this definitional equality because there's this conflict between the notation that's used in EGDA and the notation that's common in the type theory literature. But again, what I mean by this is a definitional equality. So this is the judgment that says that these things are equal. It's not identification. Okay, so this was the original perspective on identity types presented to us by Martin Liff. It relates, in fact, pretty profoundly to the point of view on equality in the traditional set theoretic foundations of mathematics, where the axioms include reflexivity and something called indiscernibility of identicals, which is can be understood as kind of a version of this path induction principle, in that it's sort of related. You know, what it's saying is essentially, once we know that little x and little y are identified, then anything that is true of x should also be true of y. So there's some sort of connection with this. But what I want to emphasize is that this is a point of view on identity types that holds for any type A in any context gamma. Okay. So now I'm going to contrast it with the second point of view on identity types, which is that for a particular type, so this is point of view number 2. So for a particular type in a particular context, type A in a particular context, you might know already how the term should be identified. In the context, you might already know how to identify terms, or know how you want to identify terms. Or, I mean, you know, there's this philosophy that says that when you're defining a mathematical object, to fully specify it, you should also be able to say when 2 instances of it should be regarded as the same. So this is part of that philosophy: know how to identify terms. And so terms. So in other words, so a type family might be given, a type might be given a type family that provides these desired identifications. So type, let me call it A, might be given and the terminology that Egbert's used is an observational equality type family. And Egbert, since you're here, I might actually put you on the spot if you don't mind. Why do you call these observational equality types as opposed to observational identity types?
Oh, I might call them observational identity type. I just wasn't aware of this.
Well, I don't.
used to it.
I don't know either. I mean, I don't have enough of a sense of the literature. The phrase observational seems to be fairly standard in this context, but I guess if you want to argue that they should be observational identity types as opposed to observational equality types, we might not argue against you, but observational is a good term in any case.
Yeah, that comes from Thorsten, I believe, observational equality. So I think I just stuck with the term that's available in the literature here.
Great. So, but the point again is that we're not distinguishing between equality and identity. That's not what's happening here. But this observational is that in this particular instance, we observe this type and we observe what its identification should be. So let's give an example. And this is an example that you've seen before, but it's maybe been a little while. So observational equality. Here, equality is a pretty reasonable term because, observational equality on the natural numbers. So this has the form of a type family, defines a type family. We can call it EQN. So here, equality is a pretty reasonable term. So for reasons that we'll discuss in the next lecture, the type of natural numbers is what's called a set. A set is a technical term in type theory that I'll introduce next time. And identifications in sets are commonly called equalities. And so here that is precisely the right term, which may be defined by induction. Defined by induction. And I want to sort of pause before I give the definition by induction and point out that something interesting is happening here. So we'll come back to this a little bit later, but the natural numbers were defined as an inductive type. meaning that they have an elimination rule that's kind of similar to the elimination rule for the identity types that we just saw. That's another inductive type. And it allows us to map out of the natural numbers and into any type whatsoever. And in particular, this U here is the universe. So the universe is itself a type, and therefore this induction principle is powerful enough not just to define functions from n valued in some other similar type, but functions from n valued in the universe. So we can use this induction principle to define type families over the natural numbers. And that's a pretty powerful thing. And I'll have more to say about the kind of extra strength of that induction principle in a minute. But in any case, we're going to define this observational equality type by double induction. And so actually, I want to make this a little bit participatory. So for those of you who are here live, would you go into the chat and rather than chat to everybody, send a private chat to me. And what I'd like you to give me is a definition of this observational equality type in the following cases. So we're interested in identifications between 0 and 0, and then between, say, the successor of some natural number m and 0, and between 0 and a successor, and then finally between two successors. So in the private chat, this is a way to let everybody think about this without spoiling the fun for anyone else. Send me a few chats how you would define these types. So here I'm asking you to assert your particular point of view on what identifications between natural numbers should be. We're using induction to just define this in certain cases and therefore define the full type family. I'm going to hop over to the chat and see if anyone is following instructions. Yeah, I guess you could send it to the host and panelists if that's easier than to just, nothing is cheating. This is just for fun. You know, sometimes it's nice to kind of be asked to think in a lecture rather than just let it wash over you. Great. And one of the things that's a little confusing is, you know, what sort of thing should this even be? You know, what am I asking you to do here? I mean, this is kind of remembering one of the things I'm asking you to recall are, you know, how we're thinking about types as encoding mathematical propositions. I mean, usually equality is like a predicate. It's either something that's just true and false. This is something a little bit different in that we're asking you to define a type that somehow encodes this logical idea. And that's exactly right. So several of you have suggested things to me, which I think is really wonderful. So the definition that we've seen in the past is, so we would like firstly 0 equals 0 to be true. So this EQN00 is meant to be a type family that encodes the true proposition that 0 is equal to 0. And one way to do that is to define this to be the unit type. So the unit type is the free type with a term that would then witness the truth of this proposition. So equally, we expect that the successor of a natural number in 0 to not be equal. So we want this to be a type that has no terms, because a term in such a type would be interpreted as a proof of an equality. So we're going to define these to be the empty type. So these are the free types that have no terms. And then finally, whatever the equality between the successor of m and successor of n should be, you know, that might be true, that might be false, but it's a clever observation that it's the same as the equality between m and n. So we can, this is a valid inductive definition. Great. So this is one instance of observational equality. The idea is that, you know, we're familiar with the natural numbers. They're kind of old friends. And so we have a sense also of when two natural numbers should be identified. So another example is given types A and B. And here I'm allowing my types to be arbitrary, but pretend these are types you know, and B. We have a sense of what identification should be in their coproduct. We may define, again, a notion of observational equality or maybe observational identity observational, but I'll stick with observational equality for today, just because that's what's in the notes for the type A plus B. So this is the co-product of those types. And this is again being a type family. So I'll write EQ plus AB. So this is a family that would take a term of the coproduct type and then a second term of the coproduct type and return a type that is the identity type or equality type between them. So once more, we can define this by induction on various cases. So remember, coproduct types have an induction principle that says it would suffice to map out of them by assuming a term on the left-hand side or a term on the right-hand side. So once more, to define this family of types by the induction principle for coproduct types, it suffices to consider the following four cases. One is when I have two terms that come from the left, so two terms of type A included on the left. So another instance is when I have two terms of type B included on the right. And again, in the chat, I'm going to ask you to propose definitions here. So these are two terms that come from B and are included on the right. That's what NL and NR refer to. And then there's the mixed cases. So I'm curious also to know what an identification between a term on the left and a term on the right must be. And because I'm defining this type family, there's sort of no guarantee that it's symmetric in any way. So I certainly have to also consider the case of an identification between a term on the right and a term on the left. Okay, so once more, to define this observational identity, we're assuming that we have some sense in what these are. And great, I'm seeing some suggestions already away. And so if A and little a both come from the type A, then I could use their own identity type here. And I declare the observational equality type and the coproduct to equal that particular identity type. We'll use the same trick on the other side. Now, when A and B come from two different types, we do not have an identity type between them, just because that's not how the formation rule for identity types works. But in any case, the way coproducts are meant to be disjoint unions, there ought not be any identifications here. And so similarly with the observational equality and the natural numbers, we'll define those to be empty. So what our goal is today, so this is the end of the intro. So our aim today is to develop a technique to identify, to prove that observational type families, when defined appropriately, are equivalent. Or maybe I'll say this is a technique to recognize when another type family is equivalent to an identity type family. So for instance, we'll apply that technique in both of these examples later on, is equivalent to an identity type family. And this is just going to be a really useful identity type family because, somehow we don't know all that much about the identity type families. We have these wonderful rules for them, but if you're asked to produce any terms in an identity type that aren't REFL, that's really quite challenging. And we've seen some of this already. In Ulrich's lecture series, you were asked to produce terms in identity types of sigma types. And unless you get lucky and the term you're looking for is a reflexivity term, there were no strategies to identify or produce any sort of identifications in a sigma type until we characterized the identity type family for sigma types. We showed that an identification between two pairs in a sigma type is given by a pair of identifications, one in the base and then one in the fibers involving some sort of transport. And really that information was kind of a necessary first step to really do anything non-trivial with that identity type. And we'll see that theme sort of over on. Great. Okay. So how are we going to do that? So again, what I want to identify is, every, these are really equivalences that I'm going to construct between a family of types. So in order to do so, we first need to introduce and study general families of equivalences. And again, what I mean by this is, for instance, when I'm going to prove an equivalence between the observational equality type on the natural numbers and the identity type on the natural numbers, I want to show that for every m and n, that this EQ mn is equivalent to the identity type between m and n. And it's the sort of for every business, that means is what I'm referring to by talking about families of equivalences. Okay, so let me give the definition. So this is a technical result that we'll need to prove our main theorem today, but it's also generally applicable, and it's not frankly that hard. So for any family of maps, and by family of maps, what I'm going to refer to as a term in this dependent function type. So for every x and a, I'm going to have a map from b of x to c of x. So b and c here are two different type families over a. And it's common not to write this last set of parentheses that I've just added in, but I'm going to add it for emphasis to contrast with the thing that we'll see in just a second. So this family of maps means for every little a and a, f of a is then a map from b of a to c of a. So there is another map. There is a map that we can think about as sort of the total version of f, tot f, whose domain is the sigma type, or the dependent pair type, and whose codomain is this second sigma type. And again, it's common not to put any parentheses here, but I'm going to add them for emphasis. So this second function tot takes in a term of the sigma type, or by induction, a pair comprised of a little a and a, and then a b in the fiber over that a, and then returns pair. But this is meant to be sort of just the fiber-wise version of the map f. So this is defined by, so tot f is going to be a particular map between these total spaces, defined as follows. And again, by induction, if I'm mapping out of a sigma type, I can assume that I'm mapping out of a pair. So for all x, y, so this x is a term of type A, and this y is then a term of type B of x. I'm going to, well, I can plug in my x and y into my f, and then that is going to, oh, it already messed up. So sorry, I'm landing in a sigma type, and I'm going to land in the sigma type in the sort of the same fiber. So this first projection is onto that same term x of type A. And then I'm going to take my f of xy as the term in here. So this is just sort of the map between these total spaces of this fiber-wise map below. And here's our theorem about families of equivalences. So for any family of maps, so for any family of maps, that was our name for it, for f, but I'll write it again. For any family of maps f, so that's our map that for any x and a provides a map from fiber b of x to fiber c of x. Then the following are logically equivalent. So meaning one is true if and only if the other is true. So the first statement is that f is a family of equivalences. And by family of equivalences, what I mean is that each map, so f of x from b of x to c of x, is an equivalence for each x, and equivalence for each x. And then the second of these equivalent statements is that this map tot f is an equivalence. So that's a wonderful thing about this totalization, is that it is exactly something that tells us that each map in this family is an equivalence. Okay, so before I go on, I want to comment a little bit about the framing here. I said blah, 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 the following are logically equivalent. So each of 1 and 2 can be expressed as a type. So there's this type family is equiv that you've seen. So the statement number 2 is saying is equiv tot F. Ulrich described various equivalent ways to define the predicate that asks whether a map like tot F is an equivalence. So this is the name of a type. This first statement can also be encoded as a type. What it says is that for all X and A, the map f of X is an equivalence. So this can be formed as the product type of these is equiv types. And what I'm asserting here is that there's a function from the one to the other and a function from the other to the one. That's this notion of logical equivalence between types. Now, it turns out, at least assuming something called function extensionality that we'll see very soon, that both of these types are propositions, which again is something that we're going to define very soon. And so these two types, in fact, are equivalent. But what I'm actually proving is that just a logical equivalence, and that's what we're going to use. So that's why I'm saying that the following are logically equivalent. But if you wanted to say that the following are equivalent, that would be true as well. It would just, you'd have a little bit more to prove in that case, and I don't want to bother with that. Okay, so there's kind of a nice high-level way to understand the proof that I'll give first, and then there's some more details that we'll discuss. So the first, right, so a thing to recall is that equivalences are, so in some terminology that Ulrich introduced, are contractible maps, meaning maps whose fibers are contractible, meaning maps whose fibers are contractible. So that's really what's at stake here. To show that the totalization is an equivalence, I need to show that its fibers are contractible. To show that each of the maps f of X is an equivalence, I need to show for each X, the fiber of f of X is contractible. So it would suffice to prove, so it suffices to show for each X and A and each, let's call it C in C of X, that the fiber of the map f of X over the point C is contractible if and only if the fiber of the map tot F over the pair. So this is the fiber of the map tot F over the pair XC is contractible. So I'm using some sigma induction here to reduce all fibers of this totalization map to just fibers over points that arise as pairs. And it turns out these fibers are equivalent. So the reason that one is contractible if and only if the other is contractible is that in fact they're equivalent as types. It turns out these fibers are equivalent. So in other words, the proof of this theorem is completed by the following lemma that is going to assert the equivalence between the fibers. And what I want to point out by stating this lemma is I'm going to state it slightly more generally than we need it. So we're using it here just in the case of a pair, but to prove it, I'm going to generalize and say for any family of maps, so exactly as above. So F is a map for any X and A from B of X to C of X, and any term and any term. So we need this in the case of a pair, but I'm going to let T just be a general term of a sigma type, X and A C of X. There is an equivalence between the two fibers that I mentioned above. So the notation is going to be a little bit worse. On the one hand, I'm interested in the fiber of the totalization function just over this term t. And what that's going to relate to is the fiber of just the function f at the first component of t. So PR1 of t projects out to the first component of t over the point which is obtained by applying the second projection, PR2 of t. So there's an equivalence here. And the reason for generalizing this statement before proving it is that it makes it a little bit easier to prove. So if the proof proceeds then by writing out the definitions of these fibers. So a fiber is a sigma type involving, so we're taking the sum over the domain of the function, and then we're looking at an identification between the point that the fiber is over and the image of the domain under the function. And by freeing up this endpoint, by sort of quantifying over an arbitrary term of this type, that's going to allow me to use path induction to reduce the identification to the case of reflexivity. And that is involved in defining both functions in the equivalence and also both homotopies. So this is by a lot of induction. So I've written a few more details in the lecture notes, but I think I'll leave them to the lecture notes because I can't imagine there's anything that I'd say at this stage to clarify. But except for this point that I'm trying to make, which is that even though we only care about this result in the case where T is the pair, it's actually easier to prove in general because it will allow us to apply path induction to get rid of the identification. Okay. But the main takeaway is we have this way of understanding families of equivalences. So a family of maps is an equivalence, meaning each component is an equivalence if and only if this totalization is an equivalence. And so now we can apply this in the case of interest. So we've reached the fundamental theorem. Or really, we've reached the definitions we need as preliminaries to understand the fundamental theorem, but this is the main event today. And what this fundamental theorem is going to do, so the fundamental theorem for identity types really characterizes a one-sided version of the identity type family. And I want to start by just focusing a little bit on the structure of the one-sided identity type so we know what we're looking for. So the fundamental theorem characterizes one-sided identity types, characterizes one-sided identity types. And what I mean by one-sided identity types as opposed to two-sided is the following. So I'm going to actually repeat the rules, but I'll present them in a slightly different way, a little bit more formally in type theory, and also present them in their one-sided form. So what the one-sided identity type looks like is, I'm assuming I have some sort of arbitrary context that provides for me a type A and also a term little a. So we're fixing one of the terms on which the identity type family depends and kind of moving it into the context. And then we'll leave the other one as being variable. So the formation rule for the identity type in its one-sided form looks something like this. So I'm thinking of this identity type family, A equals X, as varying over X, where this A is kind of back in the context already. And so that's sort of what I mean by one-sided identity type. So this is a family of types over a single variable X of type A, because the other term in the identity type is kind of already provided by the context. And so similarly, from this point of view, the introduction rule that provides reflexivity just looks like this. So the context gamma already knows about the term A, so it will just know about this reflexivity term, identifying A with A. And then the elimination rule, we're going to eliminate into families of types that depend on a single term of type A and a single identification with the little a that's already provided by the context. So what that will look like is something like this. If I have a family of types that can depend, of course, on the full context, because that's what's giving us the information about the little a, for instance, but then also an identification between little a and X, So I have some family of types P, X, P. Then we have our path induction function, which I'm going to call now path induction sub A, because we already know about the term little a from the context. And so path induction, once again, is going to give us a way to inhabit the sections of this type family. So I'm mapping into product type that says for all X of type A and for all identifications of little a and X, I have a term of type PXP. But now my hypothesis is going to suffice to give a single term, namely a term in PA REFL A. So this is the form of the path induction principle, and it's one-sided form. We're only ever considering identifications with our term little a, which is why I don't have to quantify over an arbitrary thing here. And then the computation rule has exactly the same hypotheses. So given our family of types, P, A, X, P, X, P type, then what the computation rule says is that so then gamma would know that if we took this path induction function and applied it to an arbitrary term Q that belongs to this type PA REFL A, and then to A, and then to REFL A, that would recover Q definitionally as a term of type PA REFL A. So this is the one-sided presentation of Martin-Luft's rules for identity types. And the key structures to know is that the identity type family, the one-sided identity type family, family now has the following form, has the form. So it's a family that would take a single variable, so a single X of type A, and produce a type, rather than being a type dependent on two types, it's just dependent on one type, and has a special term as a special term. This is the constructor, or it's sometimes described as freely generated as a family over A by a single term, and that's this reflexivity term. So in other words, what the fundamental theorem is going to do is it will recognize when another type family with the same form is equivalent to this one-sided identity type family. So
Emily, you're probably going to get to this in a minute, but Ryan's asking, why are we considering the one-sided identity type? Why is this useful?
Right, because the fundamental theorem is nice to state in this case. So so hold on. I do think it's a little well, let me comment on that later. So that's a wonderful question. It's very weird to, why on earth are we taking this weird kind of asymmetrical presentation of identity types here? I don't know. That's a wonderful question. Hold it in your thoughts, and I'll address it just in a moment. Okay, so we'll consider now arbitrary type families with a similar form, arbitrary type families with a similar form, families with a similar form. And what do I mean by that? So the unary identity type family is just a family over a single term of type A. So my other type family, I'm writing E because we might think of this as some sort of observational equality type family or something like this. We'll have this form with a special term that's in the fiber over little a. So this is in a context with a type. I mean, to even consider families like this, we already need to know about the type A and a term little a and A. So for the one-sided identity types, we need to know about the family that we're taking the identity types of and the term where we're sort of centering our identity types about. So if I had some other, say observational equality type family together with some reflexivity term, which we should land in the fiber over A, That's kind of the setting that we're interested in. And this this theorem will allow us to define, or maybe allow us to recognize a family of equivalences. So what would it mean for this alternate type family E to encode the identity type family? It means that we should have an equivalence. So for all X and A, I could compare the identity type that identifies A with X to this new type X. So we'd be interested in a family of equivalences here. And I can define this family of equivalences, in fact, by applying this path induction function A to R. So in other words, this family of equivalences sort of defined by sending the pair A reffle A to my special term R. So by path induction to map out of here, it suffices to give an image of the reflexivity path. And that's exactly what role this special term little r is going to do. It's going to be the analog of reflexivity in my new type family. Okay, so I'm about to state the theorem, but I need one definition for it. It's as follows. So this E and this R together have kind of the right structure to be a alternate version of the identity type family at little a. However, it does not yet have any properties that correspond to this elimination and this computation rules. You know, having the structure gives us something like the formation and the introduction rules, but we don't yet have the elimination and the computation rules, and that's what this definition is going to provide. So given a type A and term A, a type family E, so that's this proposed alternate identity type family, and term R in E of A is what's called a unary identity system. So identity system is just like another name for identity system is, we're just introducing language to describe something that is similar to being an identity type, and unary refers to that we're doing the one-sided version. If for all type families P, XP, depending on a term X of type A, and P, which is a term of type E of X. So this is like our identification for. In fact, maybe I'll call it E because that seems a little more native to this context. Call it little e. The function. So, you know, what are these elimination rules about? So they're about the dependent, or they're about sections of subtype family over this E. And so in this case, that looks like this. So here's my sections of my type family. And I have a special function, which is called evaluation at AR. So I could evaluate at my special point A of type A and my special term R of type E of A and land in P of AR. And what makes my type family E into a unary identity system is that for all families over it, this function has a section. And this section is providing a sort of up to homotopy way to express both the elimination and the computation rules of identity types. So what does the data of a section involve? So firstly, it would involve a function that goes this other way. So it would take a term type PAR and provide a section of this type family. That's exactly what this path ind A is doing above. Now, this computation rule for the identity type family proves that if I apply this path induction, so I apply this section, and then I evaluate at my special point, which in this context was a REFL A, then I recover definitionally exactly the term that I started with. So in the computation rule for identity types, I have a section where the homotopy relation is definitional equality. This is weaker than that. This homotopy relation is up to identification rather than definitional equality, but otherwise it's an analogy with the elimination and the computation rules for identity types. So I guess a way to think about this is that this section gives a version of the computational rule up to identification, gives a version of the computation rule up to identification. Okay, so let's state the main theorem, and then I'll answer the question, and then I'll give a proof. So this is now the fundamental theorem of identity types. Theorem of identity types. Okay, so what does it state? So it says, so under the same hypotheses, so for any type A, I'm doing a one-sided identity type family, so I need to start with the term A and A. And then I have alternate type family E with a special reflexivity term that lives in the fiber over my special point. So then for the family of maps, so using path induction and the data of my special term, I have a map that will take an identification and return a term of type E of X. So a name for this map would be path induction at A of R. But again, a way to think about it is this is defined by sending the reflexivity term at A to my special term R. Then the following are logically equivalent. Okay, so the first thing to say is that this is a family of equivalences. So path in A R is a family of equivalences. So in other words, for every X in A, the identity type A equals X is equivalent to this type E of X. So in other words, this alternate model is another model of the identity type. So family of equivalences. Thing two is that the total space, so the sum over X in A of E of X is contractible. And maybe I'll say onto AR. So I have a special term in this type, and I'm going to take that to be the center of contraction. And then the final point is that E is an identity system, So in other words, either of these properties being equivalent to the identity type family or having this contractible total space suffices to give this universal property that's encoded in this definition of a unary identity system, meaning for any other type family over U, there's a section to this particular evaluation function. Okay, so the question about one-sided identity types is really comes up in the second statement too. So the way this theorem is almost always going to be used is to prove that something or other is equivalent to an identity type family. We're going to prove that the total space of this new observational equality type family is contractible. And I guess maybe a way to think about this theorem, or a way to sort of check this theorem, is all three of these conditions should hold in particular for Martin Luff's original identity type family. I mean, certainly the original Martin Luff identity type family is equivalent to itself. So that's one. Two is going to be the contractibility of something that's called the based path space. So it's not at all the case. It's completely false that if you take the total path space, that in other words, you sum over terms X of type A, and then some also over terms Y of type A, and look for identifications between X and Y, there's no reason that that space would be contractible. Sometimes it's true, sometimes it's false. There's nothing to say in general. However, when you take what's called the based path space, so you insist that all of your paths start at some fixed term here, little a, then you do have this sort of contractibility. And that's really what's drawing the focus to this one-sided identity type family over the two-sided identity type family. We have this contractibility of based path spaces, whereas we lack contractibility of the total path spaces. So that's kind of an answer to the question. Okay, so the proof of this is surprisingly not so difficult. So let me give it in full. I mean, difficult given our preparation. So the first thing that I'm going to say as follows. So by the theorem about families of equivalences, so what we know is that one holds. So one is saying that this particular map that we define by path induction in something is a family of equivalences if and only if the induced map on total spaces is an equivalence, the map on total spaces. And that would be a map then whose domain is going to be the sum over X in A of A equals X, and whose codomain is then this total space of my new type family, E of X. So if and only if this map is an equivalence. However, the domain of this map, as we just, so path induction is not necessary. Sorry, I've got distracted by the chat. There's a question about whether path induction is based. It doesn't have to be, but the contractible space is this based path space. So holds if and only if this, though I guess there's a sense in which maybe there is a sense in which path induction always is based, because you know, when you're applying the path induction principle, you're sort of collapsing one of the free endpoints to the other one. So maybe there's a sense in which you're secretly applying this base path induction all the time. Okay, so right, so by our theorem about families of equivalences, this first condition holds if and only if this map on total space is an equivalence. But the domain, this right here is this thing that I was referring to by the term base path space. The domain, which is this guy, this is the base path space, is contractible. So a map involving a contractible type is an equivalence if and only if the other type is contractible. So this is an equivalence if and only if the codomain, which is this total space, is contractible. Okay. So that's the equivalence between 1 and 2. And now for 2, the equivalence between 2 and 3, I want to consider the following diagram. So consider the following diagram. So what 3 concerns is this unary identity system business, and what that is asking for is a section of the following map. So P, X, Y, I guess I called that E before, but maybe that doesn't really matter. P, A, R. So this is this map that evaluates at our special point. And 3 concerns the hypothesis that E is a unary identity system, meaning that this map has a section. But there's a closely related map where I'm regarding P as a family of types over the sigma type, sigma X in A, E, X. Maybe I'll call this T and here P of T. And similarly from here, I could evaluate at my special point, namely AR, or I could evaluate at a pair as follows. So I have a commutative diagram like this. So what this top horizontal map does is it takes so consider this is for some P that is really a family that depends on a sigma type, X in A, E of X into the universe. So by sigma induction, if I had it's even simpler than that, just by using the introduction rules for sigma type. If I had some function out of the sigma type and into P, I could evaluate on pairs and get a function from a pair X and Y into here. Then I could evaluate at my special pair AR, or I could just evaluate directly at the special pair. These are just evaluations, so this diagram commutes. And by sigma induction, so by the elimination and computation rules now for sigma types, the top map has a section. So the induction principle, again, the elimination plus computation rules for sigma types provides a section here. The map in the section is the elimination rule, and the fact that it's a section, in fact, holds up to definitional equality by the computation rules. But now it follows, thus, the left map has a section if and only if the right map does. So this is a kind of fun exercise in diagram chasing that I will leave as an exercise in diagram chasing. Section if and only if the right map does. And this is a constructive exercise, I guess, which would have to be. So using the data of a section to the map on the left, you could construct a section to the map on the right and conversely. But now let's think about what that means. So the existence of a section on the right is exactly the statement of 3. So 3, which is the hypothesis that E is a unary identity system, asserts that the right map has a section. The right map has a section. While the assertion that the left map has a section is something that Ulrich mentioned at some stage, which is called something about unit types, singleton induction. While the left map has a section if and only if whatever type appears here, which in this case is this sigma type, satisfies singleton induction. Singleton induction, which similarly was kind of the abstract up to equivalence way to describe the universal property of unit types. So in other words, this holds, this universal, the singleton induction holds if and only if, by a theorem that Ulrich mentioned if he didn't prove, this type here is contractible, which is the statement of 2 is contractible. Okay, so that's the proof of the universal property of identity types, the fundamental theorem of identity types. But the main takeaway, again, is that if we have another candidate unary identity system, and we're doing this one-sided version, so we can take these one-sided total spaces, then that provides an equivalent version of the identity type family if and only if this total space is contractible. And that's what we'll use now. Okay, so the rest of we've done all the hard work. The rest of today is just some applications. And let's start by returning to equality on the natural numbers. So I know this example is kind of familiar by now, but I think nevertheless, this is kind of nice. So, right, so let's return to this observational equality type family that was defined above, and I'm just going to copy it so I don't have to write this out again. So this was our candidate equivalent model for identity types. This was our guess or assertion of what equality should mean for the natural numbers. And now we're going to prove that it actually is equivalent to that. So there's one additional bit of information we need. So note we have a term. So we have a reflexivity term that for each n and n gives a proof that n can be identified with n. And I'll let you use the chat to tell me how this should be defined. So this is a question. Again, you can send this in the chat, either just a private chat to me, or if you want to send it to hosts and panelists, that's equally fine. So I'm arguing that sort of directly from the definitions that we gave of this observational equality type family, we can inhabit EQNN for any n. And while you're telling me how this term is defined, I'll go ahead and state theorem, which says that the canonical map this canonical map for all m in n, for all n in n, that carries the identity type family into the observational equality type family. And this map, again, is defined just as soon as I have an image for the reflexivity terms. So I can call this path ind applied to this REFL EQ is an equivalence. So in other words, observational equality does, in fact, characterize these identity types. Do folks remember how this reflexivity are defined, or should I do this? So if I'm asked, right, so I'm asking to prove great. So we're asked to define a dependent function out of the natural numbers into some type family. So a strategy to define this is using induction over the natural numbers. So that reduces to proving a base case. So for 0, I need to, yeah, so thanks for the folks who want to see a proof. That is very useful feedback for me. So for 0, I need a term that belongs to EQ00, which is defined to be the unit type. And the unit type comes with a constructor, which is canonically called star. So that's our term of type unit. And then I also need to define this in the case of a successor. So this needs to be a term of type EQ n successor of n successor of n. But this type was defined just to be EQ of n n. So assuming the induction is working out, I already have a term, REFL EQ n, that belongs to this definitionally equal type. And one of the structural rules of type theory tells us that it lives here as well. So once I have definitionally equal types, their terms belong equally to both. Great. So how do we prove that this is an equivalence? Well, what does it mean to say that this is an equivalence? It means that for all m, and then for, I guess one way to say this is it means for all terms little m, this path induction function at m is a family of an equivalence. So that allows us, even though we're considering these identity types now as being two-sided as they really are, once I fix m, I'm in the setting where I can apply my fundamental theorem of identity types. So by the fundamental theorem, it suffices to show sort of for all m in n, that if I take the total space of now the one-sided family where I'm fixing the first term to be n, so for all n in n, EQ n m n is contractible. And I want this to contract onto a term over n. I mean, using this reflexivity term, I have an inhabitant in the fiber over n, and that's where I need the center of contraction to live. Otherwise, it's possible I'm considering the wrong identity type family. Okay, so I need to show that this is contractible. And I can, well, maybe I'll just say onto my special term, which is m Riehl EQ m. So what I need is a contracting homotopy. So we'll define the contracting homotopy by induction. So this contracting homotopy, it depends on my m, and what the contracting homotopy is supposed to say is for all n and n, and for all terms e that identify m and n in the sense of this observational equality type, then I need a path from m Riehl EQM, which is my center of contraction, to the pair n e, and this is a path in this sigma type that I'm trying to show is contractible. So I'm going to define this contracting homotopy by induction on both n and m and so I'm kind of playing this game where I sort of move m into the context and pretend it's fixed for a while and then move it out so I can induct over it. This is the sort of thing that happens a lot. So in the base case, so the base case is when m is 0, and then my n is also 0. And now my e lives in the observational equality type between 0 and 0, which is the unit type. So I can induct over e and consider only the case where e is my constructor star. And in that case, this was defined to be star, and this is also star. So I can take this to be Riehl. So the inductive step is a little harder. So there's other base cases. So I'm doing a double induction, so I have kind of 4 different cases to consider. So for m equals 0 and n and some successor of n, or vice versa, I'm going to use x also, So in one of the cases where my observational equality type is the empty type, I given a term, this e is a term of the empty type, and so I can map out of it into whatever I want. So that's how you solve those cases. So for the final case, so in my double induction, my final case concerns having a successor in both of these variables and then some e. So I'm looking to define a term, which is an identification between, in this case, it's the successor of m and Riehl EQ of the successor of m and the successor of n and e. I'm going to use a map. So this is the kind of most subtle case. Thanks for whoever pointed out the typo. So I'm going to use a map. So I can obtain a term in this observational equality, or this sigma type for this observational equality type from a term here, EQ MN. So this is not going to be a fiber-wise map. This is not the totalization of a fiber-wise map. This is going to take an N and E, which is an equality between M and N, and return N plus 1 E. So this is sending the fiber over N to the fiber over N plus 1. So if I have a E, which is a term of EQMN, that also provides a term of EQM plus 1, N plus 1. So that's what this map is doing. And so this carries.
And then you also want to write N plus 1. in the second sigma type?
No, I should write K or something because it's a different variable. Yeah.
Sorry.
Yeah, I was being sloppy there, but that's a good correction. So so this term carries M REFL EQ M to M plus 1, REFL EQ M plus 1 by the way that we defined this REFL EQ function by induction. So we can apply it. So in other words, I'm going to app you apply to this function, so we can apply the map to the identification MNE to get the identification that we seek, to get the identification we need. So this last step, I would recommend just completing in a proof assistant to understand what I'm talking about. But there's something sort of a bit clever going on here. Okay, but in general, I mean, this is sort of a general paradigm for, you know, giving a full proof that an observational equality type is the same as or recovers a given identity type. So let's see some other examples. So another example that we can consider similarly is the disjointness of coproducts. So recall above we had observational equality types for the coproducts, which I'll copy the definition so we don't have to write it again. And what we can prove now is that the same relationships hold for the genuine identity type of the coproduct type, but up to equivalence. So here's our observational equality for the coproducts. Let me just go ahead and prove the thing that we'd like to show. So, well, I guess I'll state the theorem. So the theorem says that, so for A prime in A, and B prime in B, there are equivalences which are exactly of the same form as above, but now I'm going to involve the genuine identity types. So if I do the left inclusion of A and A prime, these are now terms inside the identity type of the coproduct. And this type is equivalent to the identity type in A. So this is a practically useful fact about coproduct types. Similarly, if I include on the right my B and my B prime into the coproduct, I have this in the identity type of the coproduct. So this type is whatever it happens to be, but what I can prove is that it's equivalent to the identity type from B. And similarly, I can prove that NL of A, the identity type between that and the right inclusion of some B, again, these are now both terms of the coproduct. I can prove that that type is equivalent to the empty type, and similarly if I include it on the other sides. So this is how we're going to prove it. The strategy for proving this is, again, we're going to prove that the identity type family is equivalent to this observational equality type family. And the way that we're going to prove that is, well, firstly, I need a reflexivity term to inhabit this observational equality type family. So I'm going to define, I'll call it REFL EQ once more. And this is going to be something that for any S in A plus B gives a term in the fiber over SS. So this time I'm going to define it, well, I'm also going to define this by induction, but now induction over coproducts as opposed to induction over the natural numbers. So we have two cases. I need to define REFL So induction means I can reduce to the case where my term S is of the form NLA or NRB. So in this case, I'm going to define this to be REFL A, because this, remember, was defined to be this identity type family. And I'm going to define in the other case, so REFL EQ at NRB, I get to define to be REFL of B. Okay, and now to prove this theorem, it suffices by the fundamental theorem of identity types to prove the following proposition. So for any S in the coproduct type, type A plus B, the total space, so this sum over T and A plus B of this observational equality type family at ST is contractible. And again, I'd like it to contract onto my special term, which is S REFL EQ S. Okay, and this proof is kind of fun. So, so by induction, it suffices to assume, so this is something I'm proving for any S, but by induction over the coproduct, S is in LA or in RB. I'll just write out one of these two cases, the first of them. So now the type that I'm trying to show is contractible is the sum over T and A plus B of this observational equality type between in L, A, and T. Now, this is a sigma type over a coproduct type, and there's an equivalence. This is a distributivity property of dependent pairs over coproducts between a coproduct of sigma types. So on the one hand, I can sum over X in A and look at EQ AB for in LA in LX. And I'm going to take the coproduct of that with the sum over Y and B of EQ AB in LA in RB. Okay, and then this, now I'm just going to plug in the definitions. So by the definition of these observational equality types, this was just the identity type between A and X. And this is going to be the sum of empty types. Now this right-hand sum is equivalent to nothing. So this is just the sum over X and A of A equals X. And now that's a based path space. And so that's contractible. And I can chase through the center of contraction under all of these equivalences and identify what it is in the thing I'm contracting onto. So under this equivalence, star maps to REFL at A, which includes and left into REFL at A, which is how we defined this REFL EQ in the case of in LA. And so that gives us the appropriate center of contraction. Okay, so I have 5 minutes to squeeze in a final application. So let's do it. So a lot of the homework this week concerns something called embeddings. So I'll start by giving the definition, and then we'll mention an important family of examples. So here's the definition. So a map F from A to B is called an embedding if, when I apply this to a path, if the induced map, so this is for all X in A, for all Y in A, so app F is a map that would take a path in A between X and Y to a path in B between F of X and F of Y. And the statement is that this is a family of equivalences. In other words, it's an equivalence for each X and each Y, family of equivalences. Okay, so embeddings are maps that on the identity types define equivalences. Note this is only, so in an example of embeddings that you'll see on your homework would include maps whose domain is the empty type. So this is not saying that A and B are equivalent necessarily. You can think of A as having fewer terms potentially, but whenever A does have terms, then the path space or the space of identifications in A between those terms that exist is equivalent to the corresponding path space in B. Okay, so here's the final theorem that I wanted to mention today, because this is a neat application of the fundamental theorem of identity types. And this theorem says that equivalences are embeddings. So not all embeddings are equivalences, but equivalences give examples of embeddings. And here's a proof. So suppose E, I'm going to change my notation just to suggest an equivalence, is an equivalence. I want to show then that the application of E on identity types is an equivalence. So I want to show that for all X, Y, and A, the induced map app E, which goes from this identity type to this identity type EX, EY, is a family of equivalences. So an equivalence for each X and Y. But a way to interpret what the goal here is, this is suggesting that this codomain, so that's this second family of identity types, the identifications between E of X and E of Y in B, is equally a model for the original identity type family in A. So having a family of equivalences here would say that this second type family is equivalent to the original identity type family. So I ought to be able to just characterize it by the fundamental theorem of identity types. So by the fundamental theorem, to show that this map is a family of equivalences, it suffices to show that the total space of the second type family is contractible. To show that, so I'm going to fix my X, and then I'm going to sum over Y in A, EX equals B, EY is contractible. And again, I would like it to contract into something in the fiber over EX, but I have app E of REFL X, or in other words, REFL of EX as a candidate center of contraction. So, but this is equivalent to, so if I write this type family again, so it's the sum over Y in A of EX equals B, EY. So there's an equivalence that you could construct between this type family, and all I'm going to do is turn around the paths. So using the reversals of paths, I have an equivalence between paths from EX to EY and paths from EY to EX. And the point of this is the definition of the fiber of the map E over the point EX. And since E is an equivalence, its fibers are contractible. E is an equivalence, all of its fibers are contractible, in particular its fibers over EX, points in the image are contractible. Its fibers are contractible, and that's all that we needed to show. Okay, so I'll wrap up here. Thanks so much for your attention. Next time we're going to do something very, very cool. We're going to introduce this hierarchy of complexity on types. So we've discussed the contractible types. That'll be the base of this hierarchy. At various times we've mentioned propositions, which I'll give a definition of, and sets, which I'll also give a definition of, and we'll tell you about all of the higher truncation levels as well. But anyway, that's enough for now. Thank you.
Thank you, Emily. That was very nice. Reactions are not allowed, but people can upload in the chat if they want. Are there any questions that people would like to ask now? Oh, there is a very good question there. Are sections also embeddings?
Is that in the homework? That might be. I think I'll decline to answer that one. And encourage you to do the problem set.
This is actually a difficult question.
Mhm.
Okay, so I'll stop the recording, but people can still ask more questions if they wish. Thanks again, Emily.